Good morning. So yesterday we were, so we're in this mode at the moment where we finish half a set of lectures and then start the other half set. So I'm sorry that's a little inconvenient, but I want to make best use of the time. Oh, good morning, Ossian. Welcome. This is where we were yesterday. We had this discussion about this rather scary thing called the moment of inertia tensor. That's important and a beautiful object, but we won't speak very much more about that because we understood that it is possible to diagonalize this by choosing principal axes, and then you have moments of inertia corresponding to each of those principal axes. So that will be our what we'll be making use of from now on. Finally, an important result which we did right at the end of yesterday, so let me just remind you of the bottom line, is that the kinetic energy of rotation, so if you have a rotating object, it has kinetic energy associated with it quite clearly, and that has a familiar form, a half I mv squared form, but it's given by a half I omega squared, where the I is the moment of inertia with respect to the axis about which the rotation is occurring. So here, the z-axis. Okay, so that's sort of the background for moments of inertia. So we should now get our hands dirty and calculate a few of these objects. So let's start with the simplest thing, which is a rectangular plate. And again, I can't overemphasize this. You get a different moment of inertia depending on which axis you choose. Typically for these objects, we will always choose an axis of symmetry. So let us first calculate the moment of inertia about the y-axis. Okay. So this plate is of length a and width b, and let's calculate the moment of inertia around that y-axis. Okay. So the well, not the y-axis, we start with the x-axis. Let me follow what I wrote there. So, about x-axis, so in this case we need the sort of master formula is that I subscript x is equal to, now this is a continuous object, so we use integrals rather than a discrete sum, and it's the perpendicular distance from this axis, so this is x, so we go a certain distance away, and that distance is clearly y, so we get a y squared, and then that's weighted by the mass of this element here, so dm. Okay, so Ix equals y squared dm. So we want to relate dm to the geometry of the object. So let us write dm is equal to rho, which is a density, I'll define that in a second, multiplied by the area of the element, which is dx dy. And rho, what is this? Well, rho is going to be the total mass of the object, which is big M, divided by the area of the object. So this is AB. So the object is considered to be thin. So this is a two-dimensional density. Okay, so this plate is thin. Okay, then we have that Ix is the integral over, so let's write it as a double integral now because we need to integrate over x and y, of y squared rho dx dy, and we can already put in the limits, so x is going to go from minus a over 2 to plus a over 2, and y is going to go from minus b over 2 to plus b over 2. Okay, so let us, so this is a simple integral. We're going to get a rho y to the 3 over 3 with those limits b over 2 and minus b over 2, but this is going to be multiplied by, we're also going to get the integral over x will just give us x from a over 2, well, from minus a over 2 to plus a over 2. Okay, so if you put this in, you will get, in here b over 2, that gives you a b over 8, but you have a 3 on the bottom, but you then minus the same thing, so you end up with rho a b, well, b squared over 12. Okay, so this is if you put those limits in and work out all the factors, this is what you get. We have, but we know, I mean, rho is something we introduced to do the calculation. We want to really express back in terms of the mass of the object. So substituting back in for rho, we find that I of x is going to be mb squared over 12. Okay. So that's the moment of inertia around the x-axis. Let's consider the y-axis. That's trivial. We don't need to do the calculation because it's going to be directly analogous. So it's just going to be the same result, but with a instead of b. So about y-axis, we then have iy is equal to m a squared over 12. Okay. So slightly more interesting is the case we consider the z-axis. So the z-axis is the axis out of the screen, the axis pointing towards you. So about z-axis, what will be different here? Well, again, it's going to be rho, but the perpendicular distance is now not x, not y. It's given by d there. Okay, so it's that diagonal line in the screen. So that's d squared dx dy, and d squared is clearly x squared plus y squared. So this is again, if I, well, this is really a double integral. So we have rho x squared plus y squared dx dy. The limits are the same limits as before, so let me not be lazy and not write those in. Just same limits as before. So now if we do this integral, we will get firstly the integrating the x contribution. This is going to give me rho rho b x cubed over 3 a over 2 minus a over 2, and then the y1 will give me plus rho a y cubed over 3 plus b over 2 minus b over 2. Just check that. Yeah. So this is the integral of the x, and the integral of the y for this term trivially gives me the b, and vice versa for the other term. So again, substituting back in for rho, we find that I of z is equal to big M a squared plus b squared over 12. So we note actually that this is larger than both this and this, so it will actually be harder work to spin the plate around the z-axis than either of the other two axes. The apparent mass, we can use that word, will be larger for such rotation. Let's consider another object. Now this is a thin disk. We want to calculate the moment of inertia through an axis coming out of this disk. So initially, so let's consider this disk to be initially just two-dimensional. So the axis is pointing towards us, and that will be the z-axis. So this is a 2D disk. Then IZ is going to be perpendicular distance is r, and the element is this ring here, dm. So the integral is r squared dm. It's clearly between r, little r equals 0 and little r equals big R. As before, we want to do this in terms of the geometry rather than the mass. So what do we have here? Well, the suitable element to choose, and we've already made that choice, is this ring, this annulus. So what is the area of this ring? It's 2 pi r dr. So it's 2 pi r dr, and the total mass, therefore, is that area times the two-dimensional density, which we will call rho. And rho is going to be, again, the mass of the object, big M, divided by the total area of the object, which is pi big R squared. Okay. So the IZ then can be written as 2 pi rho, the integral between 0 and big R of R squared. And now we've picked up another R, so that's R cubed dr, which gives us 2 pi rho r to the 4 over 4, which is then putting, substituting in the limits, substituting back in for rho, we get this to be a half big M R squared. So that's a two-dimensional disk. Let's just cautiously see what happens if the disk is has some thickness. So thin disk with thickness, what do we call it, T. Then what is the mass of the, so the calculation is the same, but the element of the, but dm now in this case is going to be rho times the volume element, dv if you like, and what is the element of the volume? Again, we'll use a ring, but this ring will have a finite thickness. So it's going to be rho times 2 pi r dr dt, okay? So we have to integrate over t as well in our calculation, but that integral is absolutely trivial because there's no dependence on t. We'll just get a t coming out of it. And in this case, rho is going to be the mass divided by the total volume, which is pi r squared t. So if you turn the handle, and if you forgive me for just going straight to the answer because it really is trivial, you, let me write the intermediate sum because it's, so Iz is 2 pi rho, the integral from 0 to r and from 0 to t of r cubed dr dt. And so now that the next step I will skip, and I'll just write down the answer because the answer you'll be able to see very, very obviously is just the same as before. A half mr squared. So the same. So even whether it's a two-dimensional object or a disk, it has the same result. Right, so let's complete our tour of these canonical objects by now considering the moment of inertia of a solid sphere. So this obviously has this is completely symmetric, so all we do is we define an axis passing through the center and we ask can we calculate the moment of inertia of this object. Now to do this we can actually be lazy and make use of the work we have just expended, because we note that the sphere can be seen as being made up of a succession of disks, right? So here's one disk drawn, and you can imagine adding up more and more and more. So we know what the moment of inertia of each of these elemental disks is, so we just have to sum those up. Right. So, to be clear, we imagine sphere being made of many thin disks. So they will each disk will contribute the following. A moment of inertia, which is di, the contribution of the elemental moment of inertia, and then it has a mass dm, but the moment of inertia is a half x squared dm. Okay, so this is the this same result here. But you see that for this disk, the radius can be written as x, because this is how I define my axes. Hence, once more we want to introduce a rho, and the rho is going to be the total mass of the sphere divided by 4/3 pi r cubed. And if you put this in, you'll find that then that di. Hang on. What am I looking at? 2/3. Oh yes. So we have. So dm then is going to be given by. What is it going to be given by? It's going to be given by the elemental volume of this disk, which is going to be the area of the disk. So that's pi x squared multiplied by the height of the disk, which is dz. So that gives me the volume of the disk, and then I multiply it by rho. Okay. So hence di can be rewritten as, so substituting that stuff in, pi rho over 2 x to the 4 dz. And the total moment of inertia then comes from summing up all of these disks, which is going to be a half pi rho So we stack them up from z starting down here, which is minus r to plus r. So minus r to plus r of x to the 4 dz. Now this integral needs some changing because both x and z are varying, but they are of course related. And we know just from looking at this construction that x squared is big R squared minus z squared. Okay. So x squared. So z squared plus x squared equals big R squared. Hence this. Hence I can be rewritten as I'm going to put a 2 in front because I'll change the limits of the integral to go from 0 to r. So times a half pi rho, I'm running out of space, times the integral, which as I say goes from 0 to big R now, because it's symmetric. And then I substitute x squared in, but I need x to the 4. So all of this squared is r to the 4 minus 2r squared z squared plus z to the 4 dz. Okay, so now we have an integral over in z involving just z. So this is something we can do. So what do we get? Get a pi rho in front, and then we get a r to the 4 z minus 2r squared z to the cubed over 3 plus z to the 5 over 5 between 0 and r, which, if you put everything in, you'll find this is pi rho 8/15 of r to the 5. And then, as before, we get rid of rho by and bring back in the big mass, big M, which is the mass of the sphere, and we find that I is 2/5 big M r squared. Okay, so we've worked out the moments of inertia of a variety of objects. Right, let's now go to the next lecture, which the notes were at the front for. Now, what we will consider here, that there's two very, very, sorry, it's just disappeared off the top. That says parallel axis theorem. There's two very useful theorems in this business which enable you to calculate a moment of inertia around some arbitrary axis, given you know the moment of inertia around another axis, typically around the axis of symmetry. So the first of these is the parallel axis theorem. And this is very, very straightforward to derive, so we'll do that and then we'll show an application of it. So we have this arbitrary object here, and we say it has the centre of mass is here, and we draw an axis through the centre of mass. And we can write down an expression for the moment of inertia about that axis. But we can have draw another axis parallel to that, and we can ask ourselves, what is the moment of inertia about this axis? And then we can ask, can we find a relationship between the two? Okay, so about axis through centre of mass, then we have I Cm is the integral over r squared dm. So this is our elemental bit of mass here, and it's a perpendicular distance r away from this axis. Now let us note we have this other vector defined, which is r primed, which is a perpendicular distance away from this other axis. And let us also define d to be the vector which goes from this axis to this one, which is parallel to it. So we have that r prime then is going to be given by d plus r. Right, you can see that. Let's square this because, well, let's not square it yet. Let's justify why we would be interested in squaring it. So let's ask ourselves what is the moment of inertia about the parallel axis. So about the parallel axis, we have I is the integral. Again, we consider this mass element, and this is a perpendicular distance r primed away. So this is r primed squared dm. Okay. So now we see why we might want to square r primed. So let's do this. So r primed squared is going to be given by, so dotting this vector with itself, we'll get a d squared plus r squared plus 2d dot r. Okay. So I then, moment of inertia around this parallel axis, is going to be given by the integral over each of these three terms. So d squared dm plus r squared dm plus the integral of 2d dot r dm. Okay. But this last term, d is a constant. It's just the distance between the two axes. So I can take, I can actually take that d out of the integral. So let me do that. 2d dot, and then I have r dm. And you look at this and you say, well, r dm, this is just the distance from the, so we're integrating over the mass-weighted distance from the centre of mass. And we know that is 0 because of the definition of the centre of mass. The centre of mass is what it says, it's the centre of mass. So the integral of r dm must be equal to 0. This is something we already made use of several times. So we're left with that I is d squared dm, that integral, plus r squared dm. And d is a constant. So this is just an integral over mass, so we just get big M d squared, and this is clearly the moment of inertia around the centre of mass. Okay, so this is the parallel axis theorem. We know the, I mean, it can relate to actually any two axes. Well, if we know the moment of inertia around the centre of mass, we know the distance from that to another axis, then the moment of inertia around that other axis is related by this expression. Let's make use of that by considering the compound pendulum. So what do we mean by a compound pendulum? I'm sure you know. The thing is, I mean, usually when we consider a simple pendulum, that's just what we consider to be a massless string with a bob on the end. So this object is not massless, it's like a ruler. It's one of these rectangular plates, and we revolve it around this point here, O. Okay? And we want to see if we can write down the equation of motion for this object. Now the point is, this is the pivot, we're revolving around O, but O is clearly not the centre of mass. The centre of mass will be here, and we say that there's a distance L between O and the centre of mass. And why is that relevant? Well, we know, we worked out earlier what the moment of inertia is around the centre of such an object, and now we know how to relate that moment of inertia to this one, and this will surely be useful. Okay, so let's demonstrate to ourselves that this is so. So the moment of inertia around the centre of mass is m, we're using little m here, a squared plus b squared over 12. So this is a result we had earlier. Let's see, how much earlier was it? Yes, there, it's at the top of the board. Okay. Now we can say, but we want to know a moment of inertia around O. So here we can use our new friend, the parallel axis theorem. So I is equal to ICM plus, so it's the mass times the distance squared between those axes, so that's ml squared. So this is the parallel axis theorem. Okay, so I won't write down that expression yet, but just note that we know what that is. Okay, so we want to write down a rotational equation of motion, so we're going to need a torque. So the torque about O, where what's the torque being driven by? The torque's being driven by gravity, so gravity acts through the centre of mass. So what's involved is this distance and this force and an angle theta between them. So that's that torque is going to be given by mgl sine theta, and let's be good and assign torque is a vector, so let's assign a direction to it. So it is a direction which is perpendicular to both, so that's in the k direction. If you think about it and do the cross product yourself, you'll see that it's going into the board, which is in the minus k direction. So I have a minus sign and a k there. Okay. We want to know what the angular momentum is, so J is going to be given by I omega. We know what I is, but we haven't written out the full expression yet. And I can write omega as theta dot in the k direction. So we know that torque is equal to the rate of change of angular momentum, which is I theta double dot k. So we have that I theta double dot is equal to minus mgl sine theta, and if we take the small angle approximation, we get theta double dot plus mgl theta over I is equal to 0. So that's the equation of motion. We've not yet put in the expression for I. Let's now consider what that is. So I is from the parallel axis theorem, it's given by the moment of inertia around centre of mass, so that's m times a squared plus b squared over 12 plus m L squared. Okay. The equation of motion is, it goes without saying, is a simple harmonic, and you know what the period is. The period is going to be given then by 2 pi times the root of I over mgl. It's from working out what the angular frequency is for the simple harmonic motion. And so if we put in what the expression we have for I, we have 2 pi times the root of a squared plus b squared plus 12l squared over 12gl. Okay, so that is the period of this complex, this compound pendulum. One interesting observation is that you could, okay, in general, you know, you might say, well, with this pendulum, could we measure the value of little g? And of course, in principle, you can, if you know A and if you know B and if you know L. So that is like any other pendulum. In principle, you can extract out the value of the gravitational constant at the surface of the Earth. But sometimes it might be that for such an object, we don't know what A or B is very precisely, but what we could measure very precisely is L. So let's just consider if we were to plot this time period, or the time period squared, as a function of L for whatever A and B is, what would we get? And we would get a curve such as this. And then so you see that if you draw a horizontal line across, that it crosses at 2 places. So there's a possibility of 2 lengths here, where you could, so this is the length between the pivot point and the centre of mass, and there's 2 lengths at which you would get the same period. Okay, so let us try and make use of this. So values of L give same period. So let us make use of this. So in one case, let's call it, let's talk about T1, L1, and T2 and L2. So we have T1 squared. If I just square all of that, we get 4 pi squared times a squared plus b squared plus 12L1 squared over 12GL1. And T2 squared, it's just the same thing. I'm stupidly writing it out again, but with an L2 in it. And so we're considering the case where T1 squared is equal to T2 squared. What can we then say? Well, we can say that, so we set these 2 expressions to be, well, we subtract, yeah, well, this is what we do. So we subtract, what am I doing here? This is always a good question. So let me first good. It's always good to look at your notes before you come in. Well, let me not make this statement yet, because that will look confusing. Let me just subtract. So then we get T1 squared I'm confused myself, actually. No, I know what I'm doing. I do apologise. So let's multiply both expressions. Multiply like 1 by, I multiply through by this denominator, 12GL1, and also 2 by 12GL2. Right, we're back on track now. And we also set T1 squared to be equal to T2 squared, yes. And we'll call that T. So multiplying through by this and then subtracting what we get, we will get T1 squared 12G L1 minus L2 equals 4 pi squared 12 L1 squared minus L2 squared. Okay, yes. So multiplying this by this and this by this, subtracting, this is clearly what you get on the left-hand side. On the right-hand side, notice that dependence on A and B has dropped out. Moreover, one has the difference of two squares here, so this enables us to simplify the expression and to rearrange for G, and we get that little g is equal to 4 pi squared over L1 plus L2 over T1 squared. Okay, so thank you for your patience. What we've done here is shown that we can calculate G by just measuring the period and looking at the sum of these two lengths. We don't have, there's now no dependence on the actual geometry of the pendulum. We have an expression which just depends on the distance between the two axes. So that's the parallel axis theorem. There's another one, and it won't surprise you to know it's called the perpendicular axis theorem. So this only works for actually thin objects. So we're considering a rigid object that lies entirely within a plane. We can think of three axes, x, y, and z out of this plane. And the perpendicular axis theorem relates to three. Okay. We have, so this is perpendicular axis theorem. We have that IZ, so firstly considering the moment of inertia about this axis out of this object, that's clearly given by the integral of d squared dm. But what is d squared? That is no more than x squared plus y squared dm. So just to make things very, very obvious, that's can be written as ix squared dm plus integral over y squared dm. And these look familiar. This is nothing more than the moment of inertia around the y-axis, and this the moment of inertia around the x-axis. So we have that Iz is equal to Ix plus Iy. Okay, that's one of the simplest proofs in physics. So let us show where this can be useful. We already worked out the moment of inertia of this disk, but we did that for an axis which was pointing upwards, IZ. So you remember we did this. We got the answer was a half mr squared. There it was. But now we can ask ourselves, well, what is the moment of inertia around this axis or this axis? Because to calculate these in that manner would be possible, but a bit fiddly. But we don't need to do that because we can make use of this great new theorem. So back to thin disk. So we had IZ is a half r squared, but this is equal to Ix plus Iy, thanks to the perpendicular axis theorem. And moreover, because there's nothing which distinguishes the y-axis from the x-axis, it's clear that symmetry says that Ix and Iy are the same, and so Ix is the same as Iy, and by that theorem that is going to be a quarter mr squared. Okay, very, very simple. Right, finally, I want to show a very nice result which puts together some of the things we've learnt, in particular this concept of kinetic energy of a rotating body, which we looked at the end of yesterday. So what we have is an object, I initially say a ball, but then we can generalize our result to anything, which rolls down a slope. So it's the usual story, you know, you've done this many times with a frictionless slope and for instance, a block, and you said, well, like, what is the energy, the kinetic energy of the object at the bottom of the slope? So this is the same game, but we are now allowing it to rotate. We will insist it rotates. And so this energy conservation equation must allow for the rotational kinetic energy also. Okay, so so the energy at some arbitrary time is going to be given by the rotational kinetic energy. So a half I omega squared, but it's still translating in a linear fashion, so there'll be a half mv squared, and this is the translational Ke, and then there's the potential energy, which is its height above the ground, which is mgy. So this is the Pe. Okay. Now, let us imagine that the ball does not slip. So every time it rotates, it is winding its way down the slope. So ball doesn't slip, and this therefore relates V and omega in the sense that omega is equal to V divided by big R, which is the radius of the ball. You could imagine, you know, the contrary case is if this was very, very slippery, this ball, you could start it, you could spin it at the top, and it could be spinning violently while sliding down the slope. It's not doing that. It's every time it rotates, that corresponds to motion down the slope. Okay, so hence, so the initial, it starts at rest, so its initial PE is equal to, therefore, a half I omega squared, but omega we can write as V over R, that squared, plus a half mv squared, and then I won't add any kinetic energy because I want this to correspond to the situation at the bottom. So this is at the bottom of slope. And that's where the potential energy is defined to be 0, okay? So the purpose of this exercise is to find the velocity at the bottom of the slope. It would have been useful if I had said that at the start. So where p equals 0. So v corresponds to the velocity at the bottom. So you could have trivially worked this out for a sliding block, but until a little while ago you wouldn't have been able to do it for a rotating ball. So for a sphere, what is I? Well, I is 2/5 big M R squared. This is the result we worked out. Okay. So now we know everything, and we can write an expression in terms of knowns and V. So we get mgh is equal to, write this as a half big M V squared, so taking mv squared out, 2/5 plus 1. Okay, so this is the rotational part, this is the translational part, and solving this gives root 10 over 7 gh. So that is the velocity with which the ball reaches the bottom of the slope. Finally, and very finally, I could have asked you at the start, well, imagine I have a ball rotating down a slope, falling down a slope, and I also have the same slope and I let a cylinder roll down the slope. And I could have asked you which one reached the bottom first. And if we'd had a show of hands at the start of that problem, I would guess that the answer would have been 50-50. One maybe doesn't have a good intuition for what the result is. But you see, we could calculate this for a cylinder. Which the moment of inertia of this is it's just the same as the disk. So there I is equal to a half mr squared. And if you put this in, instead of the moment of inertia of the sphere, you find that V is equal to root of 4 over 3 gh. So that is less than the sphere. So the sphere or the ball reaches the bottom first. Which is a nice result, and well, for me at least, not an intuitive one. Okay, I've overrun a couple of minutes, but thank you for your patience. So let us finish there, and we will continue the discussion tomorrow.